we have 200 kilogram object and a 500 kilogram object are separated by 0.4 meters. Right? A, find the net gravitational force exerted by these objects on a 50 kilogram object placed in midway between them. So let's do part A first. So here, since we know that this is going to be attracted to the 200 kilograms this way, right? And then the 500 kilograms this way. And the distance of separation happens to be 0.2 meters, right? And the distance of separation for these two are also 0.2 meters. Okay. So all you have to do is now just find the force of this and force of this, and then add them up factorially, and hopefully we should be able to get. So we'll call this one F200, right? And then we'll call this one F500. All right. So sum of all forces for part A, sum of all forces equal to F500 minus F200. Okay? So F500 is simply G times, right? 500 times 50, right? Oops, times 50. Divide that by 0.2 squared, right? Minus G times 200 times 50. Right? Whole thing divided by 0.2 squared. Okay. All right. So if you work this one out, I guess you're going to get something like 4.168 times 10 to the negative 5th newtons. And this one would come out to be minus 1.668 times 10 to the negative 5th newtons. So when you add them all up, your net force acting on that 50 kilograms, right, comes out to positive 2.5 times 10 to the negative 5th newtons as your. So the net force is towards the 500 direction, so it's going that way. All right, that was easy. All right, what about part B? At what position, other than an infinitely remote one, like, you know, if you put this like infinitely far away, then you won't get too much force acting on either of them. But if you were to place this somewhere in between these two masses, they're going to cancel out, right? Because the force being pulled this way is going to be great, just the same as force being pulled this way, and hopefully it's going to cancel out. Most likely, if I had to guess, it's going to have to go towards the smaller mass, right? So the force is same as the force here, okay? So if I were to redraw this, right? So here's my 200 kilogram and so here's my 200 kilogram mass, and then here's my 500 kilogram mass, right? And then the 50 kilogram mass, right, is probably going to be somewhere closer, right? So most likely from here to here, it's going to be x, and we'll make this one 0.4 minus x, right? That's the separation. So this is my 50 kilogram one. Okay? So for part B, we're looking for when net force is 0, right? We're looking for the sum of all force is equal to 0, right? And since sum of all force is equal to, right, F 500 minus F 200, and since it is equal to 0, right, F 500 is equal to F 200, right? So where can that be possible, right? So if I were to look at, right, G times 500 times 50 over this 0.4 minus x quantity squared, right, must equal to G times 200 times 50, right? Divide that by x squared. So you can see that G's can cancel out nicely. 50 can cancel out nicely, right? So I guess if you cross multiply, right, you're going to get I guess x squared, 500x squared here, right, is equal to, right, 200 times, you're going to get 0.4 minus x quantity squared. Of course, you're going to have to FOIL this, right? You're going to have to FOIL this. So once you get all that FOILed out and distribute the 200 through, right, you're going to get something like 0.4 times x squared minus 0.8x plus 0.16 is equal to x squared. Okay? And if you work this out, you're going to get 0.6x squared plus 0.32x minus 0.064 is equal to 0. Then, of course, you're going to have to use quadratic formula for this. Okay. So when you use quadratic formula, you're going to get x is equal to either 0.155 or negative 0.688, right? So I'm going to most likely pick the positive value to make it work. All right? All right. Any questions? Okay. No questions? Okay. Let's take a look at the next problem. Here we have 3 uniform spheres of mass 2 kilograms, 4 kilograms, and 6 kilograms are placed at the corners of the right triangle, as in the figure below, or next to it, right? So we have 2 kilograms, 4 kilograms, and 6 kilograms. Calculate the resulting gravitational force in both Cartesian and polar form on 4 kilogram object, right? So how much gravitational force is being influenced onto this object by 2 kilograms and 6 kilogram object, basically. Assuming the spheres are isolated from the rest of the universe. So, we're going to isolate the system, right? We're not talking about influence by gravity of Earth or Moon or Sun or anything else. All right? So, if we were to look at this, okay, the force that is being pulled this way, simultaneously, force being pulled this way, will probably result in a net force being pulled this way, right? So we could separate these in x and y components and then work it out individually, okay? So let's call this one F6 on 4. I'll make that purple, okay? And I'll make F2 on 4 as my aquamarine blue. So if I were to do, let's say, F6 on 4 is equal to G times 6 times 4 times over, it looks like 4 meters of distance, right? So 4 squared. Okay. Therefore, I guess one of the 4's can cancel out, right? And then you have 6 over 4 here, and then you could multiply that by G, and that comes out to, it looks like negative, right? 1 times 10 to the negative 10th exet. And then for F of 2 on 4, right, is equal to, right, G times, right, 2 times 4, divide that by, it looks like the separation is only 3 meters here, 3 squared. Okay? And if you work that out, you're going to get, it looks like positive 5.93 times 10 to the negative 11th y hat. Okay? So I guess, they put this in the same magnitude for the answer here, right? So this is same as saying like negative 10 times 10 to the negative 11th x hat. So that's how they factored out this term for this answer. All right. So the FG, right, the total FG, I guess, can be said negative 10, right, x hat plus 5.93 y hat times 10 to the negative 11th right? Newtons. Okay. All right. That was easy enough, right? All right. So now for part B, they want that in polar system, right? So we already know that we have this much going as 10, like negative 10 here, right, times 10 to the negative 11th. And then we have this way, right, positive 5.93 times 10 to the negative 11th, right? So if we were to sort of bring this over here and then find the resultant of that, right? So this here is the F net, right? So that's easy now, right? The sum of all force gravitational-wise is equal to square root of, right? Negative 10 times 10 to the negative 11th quantity squared plus, right? Plus 5.93 times 10 to the negative 11th squared, right? So the net force Fg is equal to, I guess you get something like 11.63 times 10 to the negative 11th newtons as the magnitude. Now for the direction, you know that this has to be measured this way, and that's your really your phi, right? And this is the reference angle of, you can make that beta if you want to. So you know the beta is equal to tan inverse of, right? Tan inverse of y over x, right? So 5.93 over negative 10, right? So you get something like negative 30.7 degrees. Therefore, your theta is equal to beta, oops, I guess you could say beta plus, now, let's make it 180 minus the absolute value of your beta, okay? Let's make it do that. Therefore, I believe you get a positive 149.3 degrees as your theta, okay? Therefore, your Fg now can be written as 11.63 times 10 to the negative 11th newtons, comma, theta is equal to 149.3 degrees. All right, done. All right, next. A student proposes to measure the gravitational constant G by suspending two spherical objects from the ceiling of a tall cathedral and measuring, that sounds interesting, doing a science experiment in a church. Okay, anyway, measuring the deflection of the cables from a vertical. Draw a free body diagram of one of those objects and use the component form forces equations to get an equation for tan theta. Okay, tan theta. I want this. So, if two 100 kilogram objects are suspended at the lower end of the cables length 45 meters long. Okay, so you know this is 45 meters long. Okay, and this is 100 kilograms. And the cables are attached to the ceiling 1 meter apart. So this is really drawn off scale. So from here to here is 1 meter apart. Okay. Calculate the deflection distance x. How much deflection is there because of the attraction of these two masses from the vertical? So assume that x is much less than 1 meter for tan theta is equal to x over a, and for r is equal to 1 meter minus 2x. So this r here is equal to 1 minus 2x. All right. So let's take a look. Let's think about what's going on with free body diagram right here. Okay. If we had this object just by itself, right? Just one of the balls. Let's see all the forces acting on this. Okay. So obviously we're going to have Fg going down, right? So we're going to have Fg going down like this. And then we're going to have tension. We're going to have tension going this way. Right? We're going to have tension going this way. This tension is going to be broken up into, I'm going to see if I can do a different color, but you know what? This tension is going to be Ty, and then we're going to have Tx. Okay. Now, this Fg and this Fg are two different Fgs. This Fg is universal gravitation between the two masses, or this is Fg between the Earth and this object. So this Fg right here, and I'm going to call that big Fg, like big G, right? Not BFG as in, like, you know, video game. Big friggin' gun, right? No. So this is what we have. Okay. Now the angle, that theta right here, this theta right here, is basically same theta as this, right? Because alternate interior angles. So I'm going to call that theta, this theta as this theta right here. So let's take a look at the y first. Right? So sum of all forces in y is equal to, right? I have Ty, right? Well, so first of all, it's equal to May, but Ay is 0, so this is going to equal to 0. And then there's sum of all forces in y is equal to, we have Ty, and then minus Fg, minus Mg, right? Because it's going down. And that is equal to 0. Ty, however, is adjacent to my angle theta. So this same as T cosine theta. Bring this to the other side and it becomes T cosine theta is equal to 0. Is equal to Mg. So if I solve for tension here, my tension becomes mg over cosine theta. Okay? So here's one of the equations that comes out from the y direction. Now let's take a look at the x direction. Okay? So sum of all forces in the x direction must equal to max, but we know ax is 0 because they're not accelerating anywhere. So the whole term goes to 0. Then sum of all forces in the x direction is equal to, right? Well, I have Fg, F big G, right? Minus Tx, which is equal to 0 now, right? So you know F big G is G times, right, M times M, they're same M's, 100 kilograms. Divide that by the separation of these two sphere, right, which is 1 minus 2x quantity squared. That's that Fg, right? Therefore, that is equal to then Tx, which is the sine of my angle theta right here, because this is my theta here. This is the opposite of my theta. Therefore, Tx is sine, right? So T sine theta. Okay? So what's going on? Well, if I were to look at this and substitute that into my T here, right? Here, I get G times M over 1 minus 2x quantity squared is equal to, right? I have mg over cosine theta times sine theta. So as you can see, one of my masses cancel out right here nicely. And this becomes tan theta, right? So G tan theta is equal to G times M over R squared, or 1 minus 2x quantity squared. Okay? Well, tan theta is actually x over L, right? So if you were to think about it, I'm going to say tan theta is equal to opposite over, no, actually, no, hold on. X over A, right? X over A. Okay? So if that's true, right, then X over A is really nothing more than square root of L squared minus X squared, right? And since X is much smaller than L, right? you could consider this to go to 0. Okay? Right? X squared can go to 0. Therefore, right, tan theta is equal to x over square root of L squared, which is pretty much L. So we can utilize tan theta as x over L. Okay? And if this is true, we can substitute that as x over L in here, right? So we're going to have g times x over L. And on this side, if we were to look at this, right, this is basically same as 1 minus 2x quantity squared. X, again, is very, 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 very small, right? Therefore, since this x is much, 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 much less than 1 meter, right? This whole term just goes to 1 meter. Okay? So when you square 1, you're going to just get 1. Okay? So here we're going to say g times m over just 1. Okay? So if we solve for x, x now is equal to, right, g times m times L over small g. Which then is equal to, right, 6.67 times 10 to the negative 11th times mass of one of them is 100 kilograms times L, which is, what's L? 45. Right? Whole thing divided by 9.8 times 1, I guess, right? So, your x, your deflection, comes out to 3.06 times 10 to the negative 8th meters. I don't know if you can measure that with physical equipment. That's like, I don't know, maybe like 100 times bigger than the width of an atom, right? So that's pretty small, right? So maybe 300 times the width of an atom, but 300 times width of an atom is still small. So I don't think there's any kind of physical instrument that can actually, like a ruler, to measure that deflection. Just saying. All right. All right. Next. (11) On the way to the moon, the Apollo astronauts reached a point where moon gravitational pull becomes stronger than Earth's. Determine the distance of this point from the center of the Earth. Okay? So we did something similar to that in the first problem, didn't we? Like this. So think about this being the Earth, and this being the moon, and then this being the, Apollo. right? It's very similar. There's no real magic in that, I guess, right? So if you want to, you can think of, so here's Earth, right? And then here's Moon, right? And then here's the Apollo, right? Spaceship. So there's going to have to be, right? Distance from the center of the moon to the Apollo, right? Well, I'm just going to call that R, Apollo to moon. And then there's going to be a distance from R to Apollo to Earth, right? All right. So the center of mass to moon to Apollo, center of mass distance from moon to Apollo are represented as that. All right. All right. Now what? All right. So here, let's think about setting these two forces equal to each other. All right. So here, I'm going to call the force this way. So F Earth, right? And then I'm going to call this way F Moon, right? And they have to equal to each other, basically, right? So and since F Earth is G times the mass of the Earth, right, times the mass of the Apollo, right, mass of the Apollo, divide that by R AE squared must equal to right, G times mass of the moon times the mass of the Apollo, divide that by radius of Apollo to moon squared. So we can actually cancel out the mass of the Apollo, and then we could cancel out the mass G, right? So if we were to solve for this relative to this, right? So let's solve for radius of the Apollo to Earth squared is equal to, by bringing it over here, it'll be mass of the Earth divided by mass of the moon. Wrong color, sorry. Mass of the moon, right? Times the radius of Apollo to the moon squared. So by putting in the values, right, of mass of the Earth, right, which is, what is that? Mass of the Earth, yeah, 5.98 times 10 to the 24th. Divide that by mass of the moon, which is 7.36 times 10 to the 22nd, times the radius or the distance between Apollo to the moon squared, So if you work this out, you're going to get radius of the Earth to Apollo is equal to, work this out, square root both sides, and you're going to get something like 9.01 radius of AM. Okay, because this turns out to something like 81.25 radius of AM. Okay, square. So since you know that, right? Since you know that, you know the radius from this has to be Earth plus the radius of the A to M, right? So you could say radius, or the distance from Earth to Moon, must equal to, right, RAE plus RAM, right? So that is equal to RAE plus, this is just simply 1 over, right? 1 over, okay, I'll move this up. 1 over 9.01 RAE, right? Because this is same as that, right? So you should be able to figure out what this RAE is relative to the radius, distance from Earth to Moon. I mean, we know what that is, right? Distance from Earth to Moon is this, right? So we can say 3.84 times 10 to the 8th is equal to, right? And add these two together, and what do we get? 1 plus 1 divided by 9.01. And we get this added together becomes 1.111 radius from Earth to Aquarius, right? Small. Therefore, RAE is equal to this divided by 1.101. All right, and that comes out to 3.46 times 10 to the 8th meters. All right. So when this is like almost like 90% to the Moon, right? That's when they become equal. All right.
Mr. Kim,
Yeah.
I think the class is over.
Oh, I'm so sorry. Guys should have stopped me earlier. Thanks. Have a nice day. We'll finish up on, I guess, Friday. All right. Take care.